Okay, exercise 4, question 1. This is a little bit longer. We're going to do all 3 parts here. It says that this TSQR is a cyclic quad. It says that SR is parallel to PQ. And it's important that TQ bisects. That means that T1 equals T2. Well, we're going to try and prove that PQ is a tangent. Well, that would mean that Q1 has to equal T1, the angle between the tangent and the chord. But we know that Q1 is equal to S2 because that's alternate angles, so we can say that. Now T2 is equal to S2 because it opens up to the same segment. We got that. But T2 is equal to T1 because TQ bisects angle STR there. So those two angles are the same. But hey, we get something out of that. From that, we get that PQ is a tangent to the circle, a TSQ that goes through that triangle. It's the converse of the tan-chord theorem because T1, this T1 right here up at the top is equal to Q1. I meant to put a little 1 there. Q1, not the whole angle Q, just Q1. Okay, so there we go. We proved the first part. Why is SQ equal to QR? Well, let's see here. We know that T1 is equal to R1 because it opens up to the same segment, SQ there. We know that T2 is equal to S2. We showed that before, the angles in the same segment. Well, that means R1 is equal to S2. And in this triangle, if those two angles are the same, SQ must equal QR, because its sides opposite equal angles. And that's it. That should be a little Q1 there. I'm going to fix that. Now, how can we get at this QS squared, TR, and SP? Well, let's take a look here. Oh, I fixed that. There it is. There's the Q1 that's actually there. Okay. QS squared and TR and SP. Well, where is QS and SP? Well, that means this little triangle here has to be part of the story. SPQ right there. But there's a TR there. Well, if there's TR and then that TQ, well, if there's a big TR here, it's just pretty likely that TQ and QR are going to be part of the story. And we know that QR and we found out that thing, the last thing that we proved back here, that SQ and QR are the same. We're going to use that. Anyways, there's those two triangles. Well, in triangle QSP, and triangle TRQ, I think they're similar, and that's going to help us get at this thing up here. So let's just try. We know that Q1 equals T2. We know that Q1 equals T2 because we proved it before. We've already made those connections. It equals T1, which equals T2. Okay, now S3 is equal to R. S3, this whole big angle here, has to equal this angle here. Well, that's the exterior angle of the cyclic quad. Well, then we know that those triangles are similar, QSP and TRQ. And we know that the S angle matches up with the R angle, and we know that the Q matches up with the T. So that's why we get the letters in the right way. We make those ratios the same way we make them every time. But what are we going to go? We're going to go with QS somehow. QS. But what was that story? QS, we're going to go with RQ because we know that RQ and SQ are the same thing, and we can just rub it out. And that's how we can get QS squared. You see how you use the thing from before to solve this funny little puzzle here. So you've got QS over RQS over well, hang on a second here. See this SP and this RQ and this QS and this TR? You just can put them together and go QS times RQ and TR times SP. That's how we get that. But RQ is equal to QS, so we can rub out the RQ and put QS. And what do we end up with? Our answer, what we're trying to prove. So you just look, okay, there's the ratios. It almost gets us there, QS, RQ, but RQ is equal to QS, and that's the big trick. You substitute that in. Oh, I've seen that. They use that quite a lot. And they use that thing from before. B was the key to figuring out question C. That thing comes up a lot.